So in this third tutorial video, I'm going to be speaking about descriptors and matching. And we're going to use a relatively simple options file for the beginning part of this talk. And we're going to be focusing on the search variable. Now, before I get into how the search variable works and the meaning of the different parameters you see on the screen, as well as the possibilities for constructing different kinds of searches in AudioGuide, I want to start just by talking about descriptors themselves. They are the metrics that we use in concatenative synthesis to measure similarity between sounds in the target and sounds in the corpus. They are, in a sense, where the magic happens, the thing that helps us transcribe one world of sound onto another. And first, before I get into talking about how to work with the program with regard to descriptors, I want to say a quick word about what descriptors are in AudioGuide for you to use. So if you go to the documentation for AudioGuide, you will see at the very bottom there is an appendix that lists all of the descriptors in the program. And you'll find a whole host of different things in this table, descriptors that describe duration and different kinds of temporal qualities like peak time and amplitude and things like that. You'll also find a bunch of descriptors that describe timbral or spectral qualities, pitch, zero crossings, different kinds of perceptual and harmonic features. All of these descriptors are available for you to use in AudioGuide. Indeed, if we run this simple example that I have in front of you, this is, by the way, using the same target from the last video, Theresa May, and the same corpus from the last video, the snare drum catalog. If we simply run this code as is, essentially we are telling AudioGuide in this code to pick the best snare drum sounds to fit Theresa May's voice according to Centroid. Here's what we get. Sorry, just a second. There we go. A quick reminder of our target sound, which is this.
Brexit means Brexit.
And if we just look at Centroid, here's what we get. But Centroid is one of many metrics, one of many descriptors in AudioGuide that you can use to evaluate similarity. Here we'll do the same target, the same corpus, now with zero crossings. And here we'll do one final one using this, this package of spectral flatness measurements, which is labeled here. So hopefully you get the idea. Essentially here, we're just changing what descriptor is used. And by changing that measurement, we have some reasonably dramatic effects over the outcome. Different sounds from the snare drum are picked to fit Theresa May's voice because we're using different measurements to pick those sounds. Before I go any further, I want to say a couple things about descriptors in AudioGuide. Let's just go back to Centroid. Generally, there are, for each descriptor, there are a couple of variations you can use, which are quite significant. So if I type Centroid, what I'm essentially asking AudioGuide is to measure the difference between time-varying centroids. Which is to say, whenever we type a generic spectral descriptor name or any of these time-varying descriptor names into a search for AudioGuide, we are matching the time series. That's what we're asking AudioGuide to do. A sound over time will have not just one centroid, but many centroids according to the analysis that trace that sound's morphological content over time. By just writing centroid, we are asking for the similarity to be calculated on that time-varying series. However, every time-varying descriptor like this one, centroid, also has a flavor or a version of it when you append the -seg argument, which essentially is going to average the centroid time-varying list into a single number. So in this search, we're searching for similarity according to a time-varying measurement. If I append seg to this descriptor, it's now going to be searching the target the target's average centroids and searching all of the average centroids from the corpus to find the best match. So that's the averaged version of centroid, and here's back at the time varying version. Time varying version is usually a little bit slower. The program's doing more calculations, right? It's not just using a single number and looking at the difference, it's looking at the difference between the time series of descriptor values. So there's no hard fast rule about which flavor of descriptors to pick in AudioGuide, whether you use the time varying version or the average version. My general approach is that I use the averaged descriptor, in this case, centroids, if I am dealing with sounds that are percussive in nature. And essentially what I mean by that is if either my target or corpus is full of sounds that don't have any temporal changes, that are just static, using the average descriptor makes a lot of sense, because essentially what you're trying to capture with the time varying version is the morphological change in sound over time. And if you've got a corpus like this one, which we're going to look at in a second, it's some prepared piano sounds. I hope. There we go. Some prepared piano sounds. There isn't really any morphological change in these sounds from moment to moment, from utterance to utterance. They are more or less static, right? And I generally tend to use the averaged descriptors when I'm dealing with these kinds of percussive sounds, either in the target or in the corpus. Conversely, whenever I've got sounds which are not static, I tend to use the time varying versions of these descriptors. In this example, both the target and the corpus have a lot of, have dynamic properties in terms of their morphological content. Speech has constant changes in vowels and noise and sound and different kinds of characteristics like pitch.
Brexit means Brexit.
You can't summarize those sounds very easily into a single idea, whereas you can do that with sustained pitches or percussive pitches. And ditto for the corpus here. The snare drum catalog also has some percussive utterances, but lots of other sounds in it that have time varying change and time varying content. And we want to capture that, if it's there, by using our non-averaged metric. So again, every descriptor, more or less, has an average version and a time varying version. And the one that is best is up to you, because it really depends on the content of your corpus. A couple more things I want to say about descriptors really quickly, just before I start actually talking about the code itself. And that is that for both time varying descriptors, there are some things you can do to essentially get some statistics or some additional information from the descriptor and measure that. So for instance, if I take any descriptor that is time varying in AudioGuide and add the delta string to it, it is going to compute the first order difference. So here, if I write centroid delta, it's going to not measure target and corpus similarity off the centroid time series, but the first order difference of the time order series, which gives us essentially the change in centroid over time. So rather than matching exact centroid values, we're going to be matching how those values change from moment to moment. You can also write delta delta, which gives you the second order difference. And I should note that these are time series transformations. So time varying descriptors take these flags like delta. And you can also then additionally append the seg argument at the end, which will do the power weighted average of the first order difference of centroids. So these strings are kind of modular and can be added together to create really specific descriptors. Here we're going to be searching for the first order difference of centroids summarized into one average. So delta and delta delta transform time varying descriptors like centroids or MFCCs or flatness or most of the descriptors in AudioGuide. It's also possible to take time varying descriptors and give some additional arguments which provide some statistics for you to use in your concatenation. And this is all in the documentation in the second table in the descriptor section, delta, delta, delta seg, delta, delta seg. And then there's also these other segmented descriptors which you can use. Essentially, if I take centroid and add min seg to it, this descriptor is going to take the centroid time varying series and give me the minimum value from it. maximum is going to give me the maximum value. And in this way, you're able to get some statistics about the time varying series, which can be computed from a single number, a similarity measurement. So here's max, centered. There's also things like standard deviation, kurtosis, skewness. Sorry, kurtosis is kurt, skewness is skew. And so while these, again, you're not matching the exact centroid values, you're matching something about how those values change in time, something about their temporal evolution rather than the value itself. So here is the skewness of centroids matched. Okay, so back to our code. Just go back to centroid, same corpus, same target. Obviously, we've talked about descriptors so far, but when you look at the search variable, it's much more complicated than just a descriptor. It's a list, and it's a list of SPass objects which have initial argument and then some descriptors that come after that. And I want to spend a little time talking about SPass, what it's doing, and eventually we'll get into sort of more complicated search structures, and I'll explain as I go why these more complicated approaches yield, I think, really effective results. So SPass is the search object. It takes in samples from the corpus and spits out some samples that are the best. In a really simple piece of code like this one, SPass is essentially taking the entire corpus of possible sounds and finding the best one, and the best one gets picked, and it's what we hear when the concatenation plays at the end of the execution of the program. SPass has the following structure. It has a method, and then in its simplest form, a list of descriptors. So you can have as many descriptors as you want, which follow your method. Here we just have one descriptor we're using, centroid, but I'll talk about multiple descriptors in just a second. But the first thing I want to sort of comment on here is that there's a method. Descriptors are the metric you use to evaluate similarity between the target and the corpus, but the method is how you tell AudioGuide how similarity is evaluated. And so in this simplest version of search, in this simplest version of SPass, we are asking AudioGuide to give us the best match, the closest one. That might sound kind of strange. Why would you not always want the best match? The answer is creative flexibility. There's a lot of interesting things to be done around the edges of this notion of exact matching. And so closest is kind of the default way to go. It's asking AudioGuide to give me the best match between time-varying centroids of the snare drum catalog and Brexit. But another SPass method is farthest. This is essentially going to give us the worst matching sample from the snare drum catalog according to time-varying centroids. And this might sound like it's going to be random or meaningless in terms of the outcome, but in fact, farthest is pretty interesting. You're essentially getting the inverse of centroids in a sense. If the centroid is high in the target, it's going to pick the worst one, which is going to be low from the corpus, right? So here's the worst matching results according to time-varying centroids. And here's, again, back to the best result according to time-varying centroids. So you can hear a kind of inversion going on there. The first one has much higher frequency content at the moments of vocal stress, whereas the second version, the farthest, the second version closest has a much lower content for those moments. So some interesting variation there, simply by changing what we're asking SPass to do with this information, with these measurements. Okay, so going back to this notion of SPass and of descriptors, one of the things I've mentioned is that you can have as many descriptors as you want. So far in AudioGuide, in this simple example we're doing, all we've measured is centroid. Let's try adding a few more descriptors. Let's add power seg and effective duration seg to our list. Remember, after the method, you can have as many descriptors as you want. And here, so in addition to just matching for time-varying centroids, we're now going to be also matching for average power. So the amplitude of the voice is going to be match to the amplitude of the snare drum sounds, and ditto for effective duration. In this construct, each of these three metrics is worth a third of the overall score, and it has a 33% control over what sample ends up getting picked, essentially. So they're equally weighted in the program in this context of writing one descriptor after another in search. So here are the results we get now. We're not just searching for centroid anymore, we're now searching for effective duration and power and centroid. I think the results here are a little better. You can hear the durations much closer. We don't get those long sounds that were being picked. And that's probably a good moment for me to point out. If you don't put anything about duration in your search, you aren't asking AudioGuide to search for duration. So explicitly, if you want things like sort of temporal features like power, peak, attack, duration to be part of what's being matched, you have to tell AudioGuide that in the search variable. So as you've probably noticed, I'm not simply typing strings for the descriptors like this. I'm wrapping them in an object that's called D. This is the descriptor object in AudioGuide. I'll pull that up quickly in the documentation. And the descriptor object takes obviously the name in quotes. That's the required argument. That's what you've seen me typing for each of these. And then it also has some keyword arguments, which you can use to tune how that particular descriptor is evaluated in terms of similarity by the search variable. So there's a bunch here that you should look at and read about in the documentation. I want to just talk in this tutorial about two of them, weight and norm. So weight is a keyword argument that you can give a descriptor object that effectively scales how important it is in the concatenation process. So when similarity is being evaluated, each of these, like I said before, has a default weight of contributing 1/3 of the sort of having 1/3 import over selection of the best sound. Here we're going to make effective duration twice as important in that. Actually, let's do it for power. We're going to make power twice as important as centroid or effective duration, effectively changing the balance of which of these three descriptors is most significant in this concatenation. Okay, so now power seg has more say over what sounds are being picked. A second keyword argument that I want to talk about that's a little bit more complicated but really important for AudioGuide is norm. By default, norm is set to a mysterious value of 2. I should actually probably have a string value here rather than something numerical, because the number doesn't really actually mean anything. It just stands for a certain kind of normalization routine. So the norm keyword is really significant. It essentially tells AudioGuide whether or not to remap and stretch the data from the corpus onto the variability that's present in the target. And to explain this a little bit more clearly, I'll give you an example, sort of an image format. So pretend that let's talk about power seg for a moment. Forget about effective duration for now. So let's just think about matching power seg. We are asking AudioGuide to pick the best corpus sound to fit a target sound according to its average amplitude. Seems relatively straightforward. Let's pretend that these are our amplitudes of our corpus and target. So on top here, this is my Theresa May's voice, and this is my snare drum catalog. So here I'm showing, let's pretend each dot is a segment. There's many more segments than this. And I'm basically trying to make the point that in this example, and many others you're going to be working with, the variation and the sort of spread of entries in the corpus according to a certain descriptor often will not match the target very well. Here, in the snare drum catalog, sounds get to be reasonably loud, but are actually also much softer in general than the target sound. And so an important question for concatenative process is like, okay, so if you want to match these two sound worlds to each other, what do you want AudioGuide to do? I think the kind of default approach is to say, okay, I'm going to ignore all of the really soft stuff in the corpus because it's too soft to match anything in the target. And the softest target sound is going to match this corpus entry here. I'm also going to basically have to pick this corpus sound over and over again when I get the louder sounds on the target, because there aren't loud sounds here in the corpus to match it. However, another approach, and this is what AudioGuide does by default, is it effectively takes this target data and scales it. It reshapes it. It changes the numbers so that they match the distribution of the things that are in the corpus. Another way of saying this is that rather than matching the exact descriptor values, the exact dynamics, AudioGuide is reshaping the target's dynamics to match the data that's in the corpus, so that rather than just using half of the corpus, it's going to use the entire thing across time. Now, this decision between either taking the exact descriptor values or scaling them and trying to lay them on top of each other is one that you can control for each descriptor independently, and you do that with norm. So if I say norm equals 2, that is the default, and this thing is going to happen. However, if I say norm equals 1, I'm going to essentially ignore all the stuff that doesn't fit in the target's initial values and only take sounds which there are sort of exact number matches for between the target and the corpus. I find that this works so much better creatively, even for spectral descriptors, even for MFCCs, yields so much more interesting and flexible results than norm equals 1, which is why norm equals 2 is the default. But there are, of course, moments that you want to have norm equals 1. So here we're going to just do norm equals 1 for power. And compare that with norm equals 2. Here the powers of the target of the voice are going to be stretched to fit the entire variability of the corpus. So we engage a much larger set of what the corpus has because we are effectively manipulating the target's descriptor data to fit the variability that's present in the corpus. So I often have norm equals 2, which is the default for almost all of my descriptors. And let's go back to the scenario we had before, which is centroid. Those were time varying. And effective duration. So I use norm equals 2, the default setting for almost all my descriptors, because I find I get better results. However, there are things where you're going to want to have norm equals 1 probably almost every time. Effective duration is definitely one of them. If norm equals 2 on effective duration, you're essentially rescaling the durations between the corpus and the target so that so that the distributions fit. In most practical applications, I think things like effective duration, you actually just want to match the exact value. If a target segment is 1 second long, you want to find a 1 second long matching corpus, for instance. This is also true for descriptors like F0, which are estimating the fundamental frequency. It's often probably the case that you want to match exact pitches, norm equals 1, rather than matching the variability of pitch over time and stretching the target's pitch content to fit the pitch content of the corpus, which is what norm equals 2 or the default setting will give you. Okay, so let's go back to this search that I've constructed. Closest segment according to time varying centroids, and equally weighted average power and equally weighted effective duration, which is normalized to respect exact descriptor matching. Now, you can get some okay results in this kind of format with AudioGuide, which is to say, listing a bunch of descriptors. In fact, I think I know people have first started using AudioGuide, they've listed like all the descriptors in a single pass to try to get really precise, exacting results. The problem with having a bunch of descriptors in one search pass is that, especially if your corpus and target aren't very similar in terms of sound content, it's really hard to find good matches where all three of these yield good results. I mean, here, snare drum is so different from the voice, right? In terms of its timbral and morphological properties. It's hard to imagine finding a sound where all three of these match really well. Much more likely is that you're gonna pretend you have a sound in the snare drum that matches perfectly the centroids of a segment of the target, but then matches really poorly the effective duration and the power. But it gets picked nonetheless because the centroids match so well that they override the poor match or the average match of effective duration and power. And this is kind of the scenario I find happens a lot when you string together long lists of descriptors for search matching. You tend to get kind of mediocre results in the middle because nothing matches all three of your descriptors really well. And because of sort of running into these kinds of problems and working on AudioGuide in the context of like musical practice, we started to look at developing other ways of designing the search that helped you provide the program with what you wanted with a little bit more precision than just giving a long list of descriptors. And this is based off some of the ideas of Norbert Schnell. But essentially what AudioGuide lets you do is not just have one S-pass, but have a couple of S-passes that are chained together. In fact, you can have as many S-passes as you want. Search is defined as a list of S-passes. You could have 1, you could have 20. And essentially the idea behind having multiple search passes is that the output of each search pass becomes the input of the next search pass. So the first search pass is going to take all of the samples from the corpus that are available. The last search pass is always going to output the one sound that wins the search. So I'm going to introduce you to a new S-pass method now called closest percent. As opposed to closest, which gives you the best sound, closest percent is going to return a percentage of the best matching sounds according to the descriptors you write, and you specify that percentage as a keyword argument, percent equals 10. The output of this S-pass is going to be passed to the next one, which is our closest. I'm going to remove these two from it. And now we get a scenario which is really typical in AudioGuide, one that I use a lot in my own work, and I think makes a lot of sense. It's a search with two S-passes. The first one evaluates the entire corpus for each target segment to try to find the best match according to power and normalized 1 effective duration. And it doesn't give us the best sound, it gives us the best 10% of sounds. Those 10% of sounds are then, the winning 10% are then passed on to the next S-pass, which evaluates them to find the best one according to Centroid. So essentially what we're doing here is we're creating a hierarchical search where we are able to define steps along the way. And this design is much more effective, in my experience, than having one S-pass with a bunch of descriptors. Because essentially you're able to say, now if the effective duration is really bad, I don't even want you to consider it to go on to the next step, in this case, Centroid. Let's listen to how this sounds. Oops, I made a mistake, but what? Looks like I'm missing a parentheses. So the durations are much tighter. In general, it sounds much better. It sounds much more like the target than other versions. Actually, just for the purposes of demonstration, I'm going to add another option to this file called cSound channel render method equals target output mix. You can look this up in the documentation. This will basically put the target sound on the left channel and the concatenated results, the corpus sounds, in the right channel.
Brexit means Brexit.
So a much tighter rendition of her prosody, of her pacing, of the sounds and the order that they come, as well as their durations, are much better respected now because we've broken the search down into two steps. One that deals with temporality and returns a percentage, and then one that deals with a timbral property. Okay, so for the second part of this video now, I'm going to pivot to talk a little bit more in depth about some examples. So in this first example, I'm going to do something a lot like what we did before, which is use the snare drum corpus from the last couple of tutorial videos and use speech as a target. In this case, we're going to be using the John Cage speech excerpt that comes in the distribution of AudioGuide. And I want to do some similar kind of search procedures that we did in the previous example, but I want to make some differences to let you know about other kinds of approaches, especially with matching the temporality of the target sound. So let's say I want to do something similar with this target that I did last time, and I want to do a couple of passes. The first pass, I'm going to try to match some temporal features, duration, amplitude, and in the final search pass, I'm going to look for something timbral. Before we do that, I want to go ahead and just open this sound file. So it's in examples of the AudioGuide distribution, cage.aiff. And remember from the first video that anytime you use a target in AudioGuide, it's going to write the real-time segmentation of that target sound file to an output file in AudioGuide's folder called targetlabels.txt. So if I run this concatenation, automatically it's going to write the target sound file labels to this file. And if we go ahead and import that in Audacity as labels, we can visually see how our segmentation worked. So go to the output folder on AudioGuide and open target labels. So these are our target segments from the concatenation from the John Cage sound file. And you can see, I suppose, more or less what you would expect, a variety of segments ranging from 0.15 seconds to maybe 1 or even 2 seconds long at certain moments. And going back to the search example, like I said, I want to construct something similar to what we did in the last one, which is to say, let's use something like closest percent according to parseg and fdurseg normalized with 1. And we'll take the best matching 10%, and then we'll pass those corpus sounds on to the next pass, which will look at centroid. So let's talk about what's good about this. What's good about this is that we're matching the temporality of the target sound first. We're then looking at the timbre of the target sound to find the best corpus sound of those that already match the temporality pretty well. But there's one small sort of problem with this approach, and that's that when you do this closest percent using fdurseg, like I'm doing now,
the lecture is so soon that I don't think I'll be able to get all 90 stories written.
you hear a lot of repetition in there. You hear a lot of the same snare drum sample being used over and over again. And that's because, and I know this because I know this corpus resource really well, overwhelmingly this is made up of short samples. As short or shorter than the shortest one that John Cage's voice breaks up into. And so that means when it's looking for the longer John Cage samples, it's got only a couple to choose from because most everything in this resource are shorter. And so one sort of approach to concatenative synthesis is to say, okay, I have a 0.7 second long target segment, I should find a 0.7 second long corpus segment, which is what we're trying to do here. However, it's also possible in AudioGuide to create, to try to recreate the target segments by piecing together or chaining together different members of the corpus, different segments from the corpus. Imagine finding a 0.2 second long sound file that matches the first 0.2 seconds really well and using it, and then picking another one after that and another one after that. A lot more like granular synthesis, I suppose, that follows the morphology of the target. They're using shorter samples. The search pass approach we're using here doesn't allow that because we're forcing it to get rid of all the samples who don't match the effective duration of the target sounds pretty well. So let's try a different approach, which does enable that kind of more piecemeal chain-like granular synthesis. I'm going to keep the closest percent in for now, but I'm going to add a third search pass to start off our search. And this is a search pass method that we haven't talked about yet called ratio limit. Ratio limit takes one descriptor, and it must be segmented, meaning it must be an averaged descriptor like fdurseg. And what ratio limit essentially does is it performs a test. It says, is the ratio of the corpus sound divided by the target sound within certain ratios? In the case of fdurseg, what it's going to do is it's going to take the corpus duration divided by the target duration. And so if the corpus segment, let's say, is half a second long and the target segment is 2 seconds long, the ratio is going to be 0.25. And then you can then specify minimum and maximum ratios, which essentially throw away or disable part of the corpus for this particular target segment. So ratio limit effective durseg, we're going to say that the maximum ratio that we will allow is 1. Translated, this basically says only sounds whose effective duration is the same as the target or less will get through this search pass. I'm now going to remove fdurseg from the search percent. And now we have a really similar kind of search in the sense that it's using the same 3 descriptors, but because we've structured how effective duration is filtered differently here, we're allowing shorter sounds to get through and making it possible to get concatenations that chain together many smaller segments. I'm just going to change the density here, which is something I'll talk about in the next tutorial, to make this outcome a little bit more obvious. So here's how this sounds with this new search method.
The lecture is so soon that I don't think I'll be able to get all 90 stories written.
So you can hear that some of the longer sounds from the corpus still make it through, but much more common is that we get a sequence of shorter corpus sounds that are stitched together by the program to try to follow the time-varying morphology of these longer John Cage segments. A couple more things I want to say about this before I move on. The first is that sometimes when you're working with collections of S-passes that are linked together, it can get a little bit confusing to understand how much effect each S-pass is having over the size of the corpus. And now's a great time for me to remind you that in the output folder, there is also, by default, a log.html file that's made. There's a lot of useful information in this. But the thing I want to mention now is that there's a section called concatenation, which has a table in it. For each concatenation selection, it shows you the size of the corpus after it passes through each one of the S-passes. So here, this table has three columns after the first one, which says what the time is of the search. And those correspond to the three S-passes in our options file. And they essentially show you how much that S-pass reduced the number of samples in the corpus by. So you can see sometimes this ratio limit doesn't do very much. It only removes a handful of sounds. Other times it does a lot. That's probably because we've got a really short target segment that discards a lot of the longer corpus segments for this particular sample. So this can help you get a better overview of the kind of progress through the corpus that the search passes are doing in terms of whittling away certain amounts of material. The second thing I want to say, which I haven't mentioned yet, is that obviously the last search pass picks your winner. It picks the sound that is selected for this given target segment at this moment. It is possible to use closest percent instead of closest. And what this will do is it will, instead of retaining one winning sound, it will retain a percentage of winning sounds. Let's just say 10. And if you have at the end of your search, the last S-pass object, if it doesn't just give AudioGuide one sound, like closest does or farthest does, AudioGuide will randomly pick between what's left. So here we can get some sort of random variations by taking 10% of the remaining 10% according to centroids and letting AudioGuide pick randomly between those. Just to make this run a little faster, I'm going to clip the target's duration to just being 2 seconds long.
The lecture is so soon.
So now if I run AudioGuide again with the identical options file, you should hear some variation in what's being picked.
The lecture is so soon. The lecture is so soon.
So another way to get some variation, some difference from rendering to rendering, is to use closest percent as your final S-pass. And AudioGuide will automatically pick randomly between the remaining candidates. So the next example, I want to pick a targeting corpus that's a little bit different than what I've been working with so far. The target sound file we're going to use is an excerpt from Kontakte by Stockhausen from the electronics of that piece. And that excerpt sounds like this. The corpus that we're going to be using is also different than something we've used before, and that is this, let's see, it looks like it's about 10 minutes long sound file of prepared piano sounds. Okay, so the first thing I want to say is that given our corpus resources, I think that this is a good time to use averaged audio descriptors rather than time varying ones. Both the target and the corpus here are percussive in nature. The sounds don't evolve, don't change much over the course of any given segment in the target or the corpus. They are more or less static. And so we're going to finish our search with the closest. Let's do MFCCs to measure timbre, but let's do MFCC's seg so that it is averaged into a single number, since that's effectively how the resources behave. So we're going to use an SPass for the closest MFCC seg as our search. And let's start off by just running this. So here we've got Contacta as the target, prepared piano as our corpus. And I'm going to run this example with simply one SPass that looks at MFCCs, which are averaged. It's actually not terrible with just MFCC seg. I'm going to go ahead and turn C-Sound channel render method to target output mix so that you can hear both the target and the output at the same time in the rendered version. Another reason I picked this corpus and target, in addition to them being percussive in nature and necessitating these averaged descriptor values, is because this is an interesting concatenation where I would argue that duration doesn't really matter. You know, I don't care in this concatenation that the prepared piano sounds hang over too long. Here's a concatenation where I'm really much more focused on onsets, and therefore I don't feel like I need to write in fdir seg, the effective duration, as any of the descriptors here, because I'm sort of happy with the corpus hanging over the target sound segment's ends. So one of the challenges of using MFCCs is that while it's very good at matching timbre, it's not necessarily very good at matching pitch or even pitch height, just kind of the relative up and down of the spectral content that we're hearing. And so I want you to try using ratio limit here as well, because one of the things I want to capture in the target is the way in which these different noise sounds kind of move up and down register. You can hear in the original sound file there's a mixture of pitch and noise. And unfortunately, that means that if we give a descriptor pass with F0, which is the fundamental frequency approximation, we're not going to get good results because the signal is not very clean and not very straightforward. Ditto for the prepared piano, who's also inharmonic a lot of the time and is not going to yield a good fundamental frequency estimate. So instead of that, to try to better capture this time varying up and down, I'm going to use centroid averaged. Again, I'm going to average the centroid with seg because of the nature of the sounds we're working with being percussive. And I'm going to do a ratio limit here. And I'm going to say that centroid seg for the minimum has to be at least 0.8. And the max ratio I'm going to specify as 1.2. So, you know, within around a whole step up or down of the centroid, so that the target centroid, any corpus sounds that are above a whole step above it or below a whole step below it will get thrown out. And then we'll pass those results on to MFCCs. So something about this pitch height kind of first to get that locked in better, and then MFCCs for timbre to try to match the different timbres of the Contacta target and map them onto the corpus. So here's what this sounds like with the two search passes, ratio limit followed by closest. You can hear, I think, a much better rendering of that kind of global contour. And this is accomplished through limiting the centroid, or sort of in a range around where the target is, and then doing something timbral after that. I should say it's important to note, ratio limit always works with average descriptors. As I said before, you can't type in centroid because you're asking it to limit based on a time varying series, which it doesn't do. And these are always non-normalized sort of raw values. So you're not, the norm keyword argument doesn't mean anything in ratio limit. Rather, it's always just working with the straight up numbers from the descriptor analysis. And for the third and final example, I'm going to work with a really different target than any of the targets I've worked with so far. This is actually a target sound file that Pierre Tremblay sent to me as a kind of challenge. And in fact, thinking about this target from the perspective of concatenative synthesis actually developed some of these features that I'm about to talk about now in AudioGuide. So here's what the target sounds like. You get the idea. Really different from the targets we've looked at so far. Things like speech, or the more musical example from Stockhausen, they are more fluid and explore descriptor space, I would say, in a more kind of unpredictable way. This target is basically a binary target. It's got two different kinds of sounds, a noisy sound and a pitch sound, interacting with each other. And I want to talk about approaches for something like this, where you've got some kind of bifurcation of content that you want to write into the search algorithm to follow a target sound that has some elements that are like this. So here I've got my options file. And so far, all I've really done is I've taken the target, I've set up the segmentation parameters. I've also built a corpus. And this corpus is a collection of the two sort of equivalents for the two kinds of sounds you were hearing in the original. I've got a folder of sort of like 8-bit sounds, which I'm going to use to represent the noise element of the target we just listened to. And then I've got a series of folders of Vienna Sound File Library sample databases that come from instruments, string instruments. It looks like I'm just using violin. And I've basically got different sustain pitches on F6, which is at least the right pitch class of the pitch that's in the original sound file. I've got harmonics, I've got non-vibrato, I've got soprano, I've got soltasto. So 4 different folders of sounds. And you can see I've also put a pitch filter on this so that even though these folders have lots of different samples, I'm only selecting the ones who have the pitch F6. That's something I covered in the previous tutorial video. I'm going to go ahead and set whole file to all of this as true, since these are all folders of sounds rather than sounds that we want AudioGuide to segment for us. And let's take a listen to what we get. Again, here's the this original sort of scratchy target. And here's AudioGuide's first attempt at a concatenation here with just MFCC SAG as being the sole search pass. So I'll turn on the target output mix thing so you can hear the target in the left channel and the corpus sounds in the right channel next time I run it. But obviously it was a bit of a mess. One of the reasons it was a bit of a mess is that all of these Vienna Sound File Library samples are much longer than any of the target segments in the target that I got. So if a target sound is 4 seconds that gets picked to match a 1 second target sample, it's simply just going to play the whole corpus sound without caring about the target's duration. There's a way to override that, and that is a keyword argument for the corpus for CSFs that I'm going to write globally here called clip duration to target. And I'm going to say it equals to true. This will, if a 4 second violin sustain sound is picked to match a 1 second sound from the target, it's going to clip the duration so it matches the target's duration. And it's going to do that for all of these corpus resources. So this will help a lot from what we heard the first time. And you also hear the target on the left and the corpus on the right. So one of the problems with this, I mean, I think in an ideal world, we would have really great sound descriptors that would just represent the binary nature of the target and classify sounds as, either pitched or noise or whatever, and then pick from the right corpus resources accordingly. Obviously, that's not happening here. And from a sort of computational point of view, as I've talked about already, search, the list of SPAS objects kind of makes this decision to say, okay, to really hone in on getting what we want, maybe sometimes you just have to write it a bit more literally than finding the perfect descriptor that will give you all the right answers. So in this case, we're going to add a new type of SPAS that we haven't talked about so far, and that is called parser. Parser is an if-then-else for descriptors. It's an if-then-else for the target descriptors. And the first thing it takes is the argument parser, of course. The next thing it takes is an equation. These are a lot like in fact, they're identical to the limit equations I talked about in the second tutorial having to deal with corpus limitations. But essentially what we're doing is we're writing an averaged descriptor. In this case, I'm going to use noisiness. And we're building essentially a little mini equation. Each time AudioGuide looks at a different target segment, it's going to run that target segment's noisiness seg through this equation, and it's either going to give the result of true or false. Then there's a couple of sub-methods that come after this. I'm going to pick the one called corpus select. And what corpus select basically says is, if this test is true, pick from the members of the corpus that I list here. If it's false, pick from the second list I give. So I'm going to write this. So when I say members of the corpus, these numbers in the lists I'm writing refer to the numbers of the corpus in the sense of the order of the listing. So I'm saying for each target segment, if the target's noisiness seg is greater than 0.5, pick from the first element of the list of corpus. Else, in other words, if it's not greater than 0.5, pick from either 1, 2, 3, or 4. Essentially what this is doing is it's saying, use the noisiness seg of the target for each target segment, use that noisiness seg value as a test. If the target passes that test, pick from this part of the corpus. If the target fails that test, pick from the other part. And because noisiness seg is going to correspond really nicely to our target sounds, we'll get, I think, pretty good results with this kind of filter applied before we get to MFCCs. I've got to write a comma there. So as you can hear, much closer results in terms of following that bifurcated target, having these two different classes of sound. And we achieved that here in cognitive synthesis by having a similarly bifurcated corpus, right? Noisy sounds, also in some pitch sounds, and then putting a test in, putting a parser in as the first SPAS that essentially removes one part of the corpus or the other according to whether the target fits that feature. You can use any feature you want for this, and there's actually other sub-methods other than corpus select. There's also a method that lets you switch what descriptors you're using based on a descriptor test as well. So if you go ahead and look at the documentation, there's a whole section on the SPAS object here. There it is. And you'll find there's some discussion of the SPAS parser methods as well as a more generalized definition than the one I've given you now. So an if then else that helps parse the target into two groups and then gives you control over how those two groups are treated. In this case, which corpus entries are valid based on the test. Now, one of the challenges, of course, with this is that it's hard to know what noisiness seg is going to be for this given target at any given moment. It's hard to know the right value to pick here. I know intuitively what I want, but I don't necessarily know the raw number. And so one thing that will help you with that is there is something called target segment labels info. By default, when the target gets segmented, we saw this before. I opened this target labels file. It's going to put some information about the segmentation in. However, if you add this variable to your script and give it a segmented descriptor name, it will put the value of that descriptor into each target segment. You'll see what I mean. I'm going to run this again. And now, as opposed to having segmentation information, my target now has the noisiness seg for all of the target segments. So you can look at this, especially in Audacity, and get a good sense of the target's variability in terms of noisiness and find the right number to pick, which will act as that, that test threshold. So I'm just going to open the target in Audacity. I'm going to import the labels just like I did before in the AudioGuide output folder. And we will see the noisiness seg, average noisiness for each of these target segments. So this can help inform your decision about what threshold to pick. As you can see, the really pitched sounds have a very low noisiness, and the very high sounds have a really sort of crunchy sound. So that's the third and final example, using parser as a way of splitting the corpus effectively into two and picking from one part of it or another part of it, depending on if the target segment in question passes a test. That's all for this tutorial. Next time I'm going to be talking about layering and polyphony in AudioGuide, something that really I haven't really addressed yet. It all deals with this superimpose object and the different ways that you can structure its keyword arguments to create different amounts of density or rarefied results. So really active concatenations with lots and lots of samples that are overlapping, or much more rarefied concatenations that have fewer elements. We'll talk about them all in the fourth tutorial on layering and polyphony.